This is the 6-1 to 6-3 review. Number 4, calculators are not allowed. And for all 3 of these, we have a solid with a circular base of radius 5, and then based on that bottom solid, or that bottom region, we're going to build a solid with a shape that has cross section. So this is a 6-2 skill 1 problem, and we will begin with, I think I'm going to do my axes in pencil because that pen isn't quite showing up as well. We have a circle with a radius of 5. And we want a cross section that is perpendicular to the y-axis. And then off of that, we're going to build an equilateral triangle. So, just like we've practiced, we're going to label the strip and the boundaries and the intersections. Radius is 5. So the equation for the circle is x squared plus y squared equals 25. Because we've cut horizontally, we want to have that strip labeled with y's, so that means I would need to isolate the x's so that I can replace x's with y's. X is going to be plus or minus the square root of 25 minus y squared. So if I label this here, my y coordinates are the same, and this one is the positive root, whereas this one over here is the negative root. So now the length of that strip, which is the same as the base of the triangle, is going to be the right x-coordinate minus the left x-coordinate, which will be the root minus the negative root, will actually give me 2 of those roots. And then in order to find the volume of this slice, I'm going to need the height of that triangle. So remember, this is an equilateral triangle, so the 3 sides are the same. These angles are all 60s, so when I drop an altitude, I'm going to get a 30, 60, 90, and the height of that 30, 60, 90 will be the short leg, which is half of this, times a root 3. So the height is going to be half of the base times a root 3. Now some of you are going to want to distribute that root 3 in, and I urge you not to, because it'll make it more difficult to evaluate the integral. So what we're going to do now is set up that integral. The volume integral will be a 1/2 times the base times the height times the thickness, which is a dy. Now normally we would drag this strip all the way down and all the way up, and we'd see that our limits are from -5 to +5. However, I want to use the symmetry of this shape and only go from 0 to 5 and then double it. Since I'm working by hand, I'd rather work with a 0 than with the -5. So we've got this integral set up. What we want to do is simplify it so that we can actually find the antiderivative. So to do that, I'm going to get all the constants, this root 3, the 2, and the 1/2, and the 2. I'm going to put those all together out in the front. So that'll give me, these cancel, I'll have a 2 root 3 times the integral from 0 to 5 of this root times this root, which will actually get rid of the root and just be a 25 minus y squared. So now I can answer the question posed by the integral symbol. What did I take the derivative of with respect to y that gave me this inside? And the answer is a 25y minus a y cubed over 3, and then I'll evaluate it from 0 to 5. First thing that gets plugged in is a 5, so that would give me a 125. Then I'll have a 125 over 3. And I don't have a calculator, so how I can think about this is if I get a common denominator, I'm going to have 3 of those 125s minus 1 of those 125s. Well, that's going to give me 2 125s. So that means I'll end up with a 2 root 3 times 2 of those 125s, which is a 250 over a 3. Finish multiplying that out, we end up with 500 root 3 over 3. Okay, so let's look at part B. Part B, it's the same base. We still have that same circle on the bottom, but we are now going to build semicircles off of it that are perpendicular to the x-axis. So, axes in pencil, curve in pen, slice in red, and this time, instead of isolating the x, we're going to isolate the y. So we have an x squared plus a y squared equals 25. It's the y that needs to be alone this time, so that's a plus or minus square root of 25 minus x squared. So if I label this, these strip endpoints, everything's going to be in terms of x this time, and the top one is the positive root, and the bottom one is the negative root. I'm going to need to move this strip all the way left and all the way right, so I'll need this endpoint and this endpoint. And now we're going to draw our sample slice. Our sample slice has this length as its diameter, and then we're building a semicircle off of it. So the volume of that slice will involve the thickness dx and the length of this strip. So the length of this strip is a root 25 minus a negative root 25 minus x squared. So I end up with 2 of those roots, which will be the entire diameter. That means the radius is going to be 1 of those roots. So I'm going to label just the radius on this, so I don't inadvertently use the wrong thing. If I now want to set up my integral for the volume, I'll have that volume equals a 1/2 pi times that radius squared times the thickness. And I'm going to add them all up from -5 to 5. Now, rather than going from -5 to 5, I could just go from 0 to 5 and double it. So I'm going to do that. I'm going to double from 0 to 5. So if I simplify that, I see I've got a pi out in front, and inside I have a root that has been squared. So the antiderivative will be a 25x minus an x cubed over 3 from 0 to 5. Now that looks an awful lot like the one we just did up at the top. So I'll have a pi times a 125 minus a 125 over 3, which means if I get a common denominator, I'm going to get 2 of those 125s over 3, which will give me a pi times a 250 over a 3.